Amazing. So we are extremely happy to have Robert Mello Koch here to speak with us today. Robert, thank you very much for taking the time. To give you a bit of context, Robert obtained his BSc in engineering. Oh, for shame. And then a PhD in physics from the University of the Witwatersrand. He completed a year of postdoctoral studies at Brown University before returning to the University of the Witwatersrand. From 2007 to 2022, he held the DST NRF Research Chair in Fundamental Physics and String Theory. Since 2022, he is a distinguished professor and Chang-Jiang scholar at Huzhou University in Zhejiang Province, China. His most recent research interests include the gauge theory, string theory duality, the application of representation theory of discrete groups, and Lie groups to quantum field theory and deep learning. We're extremely excited to have you here. Thank you so much. Please take it away.
Okay, thanks very much, Will. So my understanding is that this talk is sort of meant to be especially aimed towards students and setting up the background that's needed for next week's lecture. So that's what I'm going to try to do. There's three things.
Sorry, let me just quickly ask. Should we save questions to the end, or should people ask questions as we go along?
Oh, it would be excellent if people ask questions as soon as they arise.
Right.
So if you've got any question, please do ask. Yeah. So there's three things that I want to explain today. So I want to start off talking a little bit about gauge invariance. What is it? Why do we need it? And the reason why I want to do that is that a lot of what's going to be motivating the talk is really fixing gauge invariance completely and figuring out what the physical degrees of freedom of a system are. And hopefully by the end of this little introduction, that'll make more sense, exactly what that statement means. Then I'm going to talk a bit about partition functions, and I'm going to introduce some tools from mathematics known as Hilbert series to interpret partition functions. And next week, we'll actually calculate a partition function for certain matrix models, and we'll interpret it using what we've learned about Hilbert series. And finally, I'll be talking about trace relations. And this is going to help us to actually check our interpretation of the partition function that we meet. So it's really three different topics I want to discuss today: gauge invariance, Hilbert series on partition functions, and then trace relations. So let's start off with gauge invariance. So the argument that I'm going to try to make is that gauge invariance is needed to resolve a basic tension between quantum mechanics and special relativity. So let's start off with the scalar field. So I've got the mode expansion here for the scalar field. So hopefully that's something that's familiar. And I just want to dissect this formula, and let's look at the different ingredients that appear here. So you can see I've got the measure sitting here, integral d3p over 2 pi cubed 2 omega p. What's important about that measure, as I've said over here, is that that measure is Lorentz invariant. So if you were to change to some other Lorentz frame, you'd need to calculate the Jacobian and also transform this omega p, and you would find that in fact that measure is invariant under that transformation. Good. The other thing that appears inside this formula are these e to the minus ip dot x and e to the plus ip dot x. P dot x that is sitting there is a contraction of two 4 vectors. So P dot x is omega pt minus P dot x. Omega p is the time component of a 4 momentum, and p with an arrow is the spatial momentum. And it's contracting with a position 4 vector, which has both a time and spatial point, so that P dot x itself is also a Lorentz invariant quantity. So the last thing that appears inside this formula are these creation and annihilation operators. And how should we think about these? Well, as usual, whenever you want to specify these operators, we give an equation. What sort of an equation do we give? Something like a Lie algebra equation, okay? And this might be familiar to you when you studied non-relativistic quantum mechanics. You first of all worked out the commutators of orbital angular momentum. Then when you had those commutators, later on you said, oh, the Pauli matrices are also angular momentum operators for spin 1/2. So we used to specify operators by giving a commutation relation, And in fact, even in quantum mechanics itself, we usually specify the operators P and X by giving a commutation relation. So no different for A and A dagger. An important thing to realize about this equation for A and A dagger is that the right-hand side of this commutator is again Lorentz invariant. And that means that all inertial observers would use exactly the same set of oscillators. So what has gone in here to this scalar field equation is that you can see that I've relied a lot on Lorentz invariance. And in fact, it's largely determined by Lorentz invariance. And the transformation law for the scalar field is exactly this one that you see over here. Phi prime of x is equal to phi lambda inverse on x. And I would challenge you to now try to prove that this conservation law, that this transformation law holds, using the fact that the measure is Lorentz invariant, using the fact that p dot x is a Lorentz invariant, and that these oscillators are Lorentz invariant. You should be able to prove this transformation law. Why are we so obsessed with Lorentz invariance? Why does this play such an important role? Well, it's for the following reason. Special relativity tells us that the laws of physics should be the same in all inertial frames. So it really tells us that the content of the laws of physics should be Lorentz invariant. The laws themselves can transform covariantly, so they mix with each other when you move to some other frame, but the content of them is the same in any frame. One of the most basic things that you can require is that if any inertial observer looks at an electron, for example, they all agree that it's an electron. So if I'm at rest and I see a particle, it's an electron. If somebody's moving and they look at the same particle, they will agree that it is also an electron. For that to be the case, it means that if I take my electron state and I Lorentz transform it, I'll get the state of some other inertial observer. That must still be the state of an electron. So that means starting with a specific electron state and considering all Lorentz transformations of that state, they should all be identified with the particle. So this is why we identify particles with representations of the Lorentz group. It's the first most basic step towards making sure that the laws of physics are Lorentz invariant. Now, there's a little jump to say why should fields be in representations of the Lorentz group, but this is also something that perhaps should be familiar. If you think in classical mechanics, when we study something like F is equal to ma, they were certainly studying equations for particles. In Maxwell's equations, we study equations for fields. And in classical physics, fields and particles are two distinct ways of talking about nature. When we do quantum field theory unifies these two concepts, and the field itself is quantized. One quantum of the electromagnetic field, for example, is a photon. And it turns out that the way we think about particles are always quanta of fields, and associated to every particle, there is a field. If we want the field to transform in a representation of the Lorentz group, if we want the particle to transform in a representation of the Lorentz group, certainly the field itself must transform in a representation of the Lorentz group. So we started with the scalar field. This was a spin naught particle, but now we're going to take a look at a spin one field. And this is, in fact, gauge bosons, and this is where we have gauge symmetry is needed. So now I'd like to make the argument for why we have to have gauge symmetry. Why is it compulsory? So a vector particle will transform as in this boxed equation sitting over here. And what you can see now is a mu prime is equal to this matrix lambda that represents the Lorentz transformation. So this is the matrix that you would have written down before with Koches and cinches and causes and sines. That's just the matrix representing the Lorentz transformation. But what you can see is it contracts with the field index. And that means the different components of the field are shuffled amongst each other under a Lorentz transformation. And at the same time, the space-time point is acted on by lambda inverse. So that transformation of the space-time point is exactly the same origin as the law that you know for the scalar field. The only difference is that now the field has many components, and these are mixed with each other under a Lorentz transformation. Because the field carries a 4-vector index, the creation and annihilation operators themselves have to carry 4-vector indices. We again want to specify them by giving some commutator. Well, what could that commutator be? So what I've done is, in this equation over here, written in black, I've given you the commutation relation that we had for the scalar field. So that's a good starting point. I then put on these green indices mu and nu, and on the right-hand side, I'll now need some tensor T mu nu. Now, just as we discussed before, we want to respect Lorentz invariance, so we would like this commutator to be a Lorentz invariant statement, so that all inertial observers use the same set of creation and annihilation operators. That means whatever this tensor T mu nu is, it has to be Lorentz invariant. And if you're looking for a Lorentz invariant tensor with 2 indices, there's a single choice, and that's the Minkowski metric. You could choose plus or minus the Minkowski metric, but it has to be the Minkowski metric. This now is a requirement from special relativity. Special relativity forces us to set T mu nu equal to eta mu nu. If we do that, the commutation relation between the time-like, the temporal oscillators, will be A naught comma A naught dagger is equal to a minus sign and what we had for the scalar field. If we look at the spatial oscillators, there's an AI, AJ dagger, and this is equal to a plus times what we had for the scalar field together with this delta IJ. And the important thing to pay attention to in this formula is this difference in sign on the right-hand side of these 2 commutators. And that's forced on you by special relativity. Special relativity forces you to take eta naught naught for the first relation, which is where the negative came from, and eta ij for the second commutation relation, which is why it's still a plus. So these signs that I have circled in yellow, they are forced on you by special relativity. So special relativity is forcing that. What I now want to argue is that those signs are in conflict with quantum mechanics. Quantum mechanics abhors those signs. So why is this bad for quantum mechanics? I'm going to consider making a wave packet of this A naught particle. So I've got ket psi. It's an integral over spatial momentum, some f of k, A naught dagger acting on the vacuum. So this A naught dagger will just produce a particle of momentum k, and f of k is going to give me some nice wave packet. If I choose that the integral of the mod of f squared is finite, then I've got a nice normalized wave packet, and I can work very well with it. And that's the choice I'm going to make. I now want to calculate the norm of the state. So to calculate the norm, I take the dagger to get the bra, and then I'll calculate the bracket of bra psi with ket psi. For the bra and the ket, I've got one integration over momentum. So I've got an integral d3k1 and integral d3k2. F star of k1 is the wave packet for the bra, f of k1 the wave packet for the ket. And then I've got this matrix element of vacuum, A naught, A naught dagger, and vacuum. Okay, and now let's change colors. As Amy Winehouse would say, let's go back to black. And now take a look at this extra term. I've just added this. So the line above, the only difference with this line over here, I've added the second term, but this is an annihilation operator. So I've added naught. Why was this a good naught to add? Because what sits inside this round bracket now is precisely the commutator. So using the commutator for the A naught dagger oscillator, I'll just get a minus. So there's the sign that we that I said is going to cause a trouble. 2 pi cubed delta function 2 omega k. This is just a number, I can pull it out. I then use the fact that the vacuum is normalized to 1, and I've just got a minus 2 pi cubed delta function 2 omega k1. Good. Let's plug in that matrix element, and now we can do the integral over one of the momenta thanks to that delta function. So we plug it in, we do the integral over, let's say, k2, and call the resulting momentum k1. And what do we land up with? Minus 2 pi cubed, that's positive, integral d3k, mod f of k squared, that's positive, 2 omega k1, that's positive. I've got a positive integrand. It's a nice finite integral if I've chosen f nicely. So the result of doing that integral is going to give me something positive. I've got the minus sign sitting up front, which means the result is this state has a negative norm. Now, that is not something that agrees with quantum mechanics, because in quantum mechanics, we know that negative norm states spoil the probability interpretation of quantum mechanics. So this minus sign that relativity has forced on us has spoiled the probability interpretation of quantum mechanics. So this simplest, naive approach, adding an index to the oscillators, has not worked. And to get a theory that does make sense, we have to remove these negative norm states somehow. But if we have to do it in a way that doesn't spoil Lorentz invariance. And how was that done? Well, that's precisely what gauge symmetry does. Okay. Just by the way, if you were quantizing something like the graviton spin 2 or some other field with even more indices, on the right-hand side, you would have even more factors of the Minkowski metric. You'd have exactly the same problem of minus signs popping up from the Minkowski metric. So for example, for the graviton, you need a gauge invariance, that's general coordinate invariance. And if you go to even higher spins, you need more and more gauge invariances to remove all of these negative norm states. So we'll talk about how that happens now. I'm not going to discuss this at full quantum level. I just want to hopefully make a connection to some things that you've already seen. So I'm going to look at electrodynamics. So in electrodynamics, I'm sure you know that the gauge transformation of A mu of x is this field that I've called A mu tilde of x. So A mu tilde of x, the gauge transform of A mu of x, is just A mu plus D mu chi of x. So this chi sitting here is the parameter of the transformation, and it depends on x mu. So it's a local transformation in space-time. Gauge invariances are always local. If we want to connect this to the kinds of things that we studied as undergraduates, well, this 4 potential, its temporal component is the usual scalar potential, and its spatial piece is the usual vector potential. Writing the gauge transformation in terms of these pieces, the usual vector potential of magnetostatics, when you gauge transform it, you get the vector potential plus the gradient of some scalar chi of our gauge transformation. The scalar potential is just given by the gauge transformation of the scalar potential is just given by the scalar potential plus a time derivative of the gauge transformation parameter. And now if you were to calculate something, so remember in classical electrodynamics, the potentials are not physical, they're not observable. The things that are observable that actually will cause our particle to accelerate are things like the magnetic field and the electric field. In quantum theory, that's not quite true, but I'm just discussing things at classical level now. So if we ask what happens to the B field under a gauge transformation, well, the curl of the magnetic vector potential is equal to the curl of the magnetic vector potential plus the gradient of chi, because the curl of a gradient is always 0. So what that means is when we did this gauge transformation, we certainly didn't change the magnetic field. And if you look at the electric field, we've got minus gradient of the potential of the scalar potential becomes minus gradient scalar potential plus d chi dt. And then we've got plus the vector potential dt. Well, that becomes the vector potential dt plus d by dt acting on the gradient of chi. And what you can see is this term over here is minus gradient d by dt on chi, and this term over here is d by dt gradient on chi. And d by dt commutes with gradient, so those two terms cancel. So the electric field also doesn't change under a gauge transformation. So what that tells you is the state of the electromagnetic field is completely unchanged classically by this transformation. It defines the same physical state. Gauge invariance is not a statement about a symmetry of nature. Okay, so what do we mean by something when we say that there's a symmetry of nature? If I show you a video, I drop a ball, I film it, and I show you that video, and I say to you, did I record the video yesterday, or did I record it last month? In fact, you can't tell when I recorded it because the laws of physics don't change as time passes. If I record the video in a rotated lab or in a lab that's aligned in some other way, you can't tell what the orientation of the lab was because the laws of physics are rotationally invariant. Those are really fundamental symmetries of the laws of nature. For those laws, I think that you guys probably already know, there's a theorem, Noether's theorem, which tells you for each such invariance, there is a conserved quantity, which we often call a Noether charge. And that's what you get from the fundamental symmetries of physics. Gauge transformations are not like that at all. So don't think of that as a gauge transformation. Gauge transformations are the statement that you've got a redundancy in your description. You're using too many variables. Over here, we saw that if we use A mu tilde or A mu, we get exactly the same electric and magnetic field. So we're using too many variables. Not all of them are physically important. And the way that gauge invariance works is it's exactly alpha naught dagger that is not physically important. It gets kicked out of the theory when you say, I only want gauge invariant quantities. So you needed the alpha naught dagger there so that you could set up things so that they were both Lorentz invariant and consistent with quantum mechanics. And to be consistent with quantum mechanics, you have to get rid of alpha naught dagger. That's what gauge symmetry does for you. So whenever you've got spin 1, spin 2, any higher spins, the only way to formulate these theories sensibly is using gauge invariance. Relativity forces you to have negative norm states. Gauge invariance gets rid of them. Just to perhaps also link this to something that you've seen before.
Sorry, Robert, just one second.
When you say you get rid of A naught dagger, do you mean you're fixing A naught dagger, or you're just not using it? Or...
So first of all, you could really, if you like, get rid of it. So you could do something called gauge fixing. So you could set A naught actually equal to naught if you wanted to, and that would be a certain gauge choice, and there would be no problem with that. Okay, so that you could do. Something like Coulomb gauge will make it manifest that you only have states of positive norm. Now, the nice thing is physical quantities are gauge invariant. So if you like, you can keep A naught dagger inside your theory, and you're worried, I've got the state of a negative norm, but any physical probability that you calculate will always come out as positive. And gauge invariance is actually guaranteeing that for you. So I could go into more detail on this. Let me maybe just say one thing, if you want to read a bit more about this. The BRST charge of quantum field theory. So you might wonder, why is that there? That's precisely implementing statements of gauge invariance, and you use that to prove unitarity. And that actually is the statement that you only have positive norm states inside your Hilbert space. Okay, so sorry guys, there's tons more that we could say here. I just wanted to give you the basic ideas. Now, think about in normal electrodynamics, you've got alpha mu dagger. So you would think, well, I can create 4 different types of particles, but you know very well that, in fact, if you look at photons, there's only transverse modes of polarization of the photons. So you've only got 2 physical states. So that shows you, out of these 4 modes that you have, only 2 of them survive actually as physical gauge-invariant degrees of freedom. So if you fix Coulomb gauge, you would only get these transverse components appearing. Now, what is slightly interesting, so when you hear a statement like that, you might think, well, why don't we just work with the physical particles and not bother with gauge invariance at all? Let's just restrict the physical particles. The reason why we don't do that is that when we say that the physical polarizations are the ones that are transverse to the direction the particle is traveling in, this statement, the direction that the particle is traveling in, is not a Lorentz invariant statement. If you go to some other frame, the particle will be traveling in a slightly different direction, and you'll have a slightly different set of physical states according to some other inertial observer. So it's really a very subtle way that relativity and quantum mechanics come together, and it's really gauge invariance that's making that all consistent. So that was the first idea that I wanted to introduce, that gauge invariance is really needed to resolve a tension between quantum mechanics and special relativity, and that if you get rid of all of the unphysical degrees of freedom, the gauge degrees of freedom, you'll be left with physical degrees of freedom, and this is like being left with only the transverse polarizations of the photon. Now, let me tell you how we're going to use that in the talk next week. So first of all, for non-Abelian gauge theories, you would again have a gauge transformation law, but it's something more like this. A mu tilde is now an n by n matrix if you're dealing with a gauge theory with gauge group un. So A mu tilde will be an n by n matrix. Under a gauge transformation, you have to take u dagger onto A mu onto u. Now u itself is also an n by n matrix. So this first term here is a product of 3 n by n matrices. And then you would say minus I u dagger d mu u. And the second term sitting over here is the analog in electrodynamics of this d mu chi term. So now even the first term, A mu changes. If you've got matter sitting in an adjoint representation, which is the kind of thing that we like to do, then this matter would be called phi, and phi tilde would be equal to u dagger phi u. What I'm going to do next week is I'm going to study this Hamiltonian for matrix quantum mechanics. You can see it's a free Hamiltonian, it's just a matrix oscillator. And I'm going to declare that phi a going into u dagger phi a u is a gauge symmetry. So I have to look at things that are invariant under the symmetry, and I'm going to completely fix the gauge. And I'm going to try to tell you what actually are the physical degrees of freedom. And surprisingly, this exercise was never done before. So you'll see what the answer is next week, and hopefully have a better idea of exactly what's involved. Okay, so that's the end of the first little bit. If there's any questions now, this would be a logical place to ask. Okay, if not, we can continue. So next I want to talk about partition functions and how to think about them. And we're going to be using some tools that come from polynomial rings. So when we study partition functions of free series, what are we doing? We're basically just counting states. And there's a nice math way to count states known as Hilbert series. And that's what I'd like to discuss now. So I'm going to give you a problem. So just count the number of polynomials of a given degree in 2 variables. So our 2 variables are going to be x and y. So if we say degree 0, well, there's just one polynomial, that's 1. If we say degree 1, we could have x or we could have y. If we say degree 2, we could have x squared, xy, or y squared. And as you go up in degree, there's more and more polynomials that you could have. And if you considered more variables, of course, then you could also have more polynomials. So how could we count these? Well, the way to understand a counting formula is to realize the following. Look at the product of 1 over 1 minus x times 1 over 1 minus y. Let's assume that x and y are both less than 1, so I can expand both of them. So this is one of the series that we did in high school. So the 1 over 1 minus x becomes 1 plus x squared, and so on, and the same for the 1 over 1 minus y. Now let's multiply out these two brackets. So the 1 times the 1 gives us the 1 sitting there. X times 1 gives us the x. 1 times y gives us the y. Let's just go to degree 2. X squared times 1 is x squared. X times y is xy. And 1 times y squared is just the y squared sitting there. So what you can see is if we expand this out, on this line over here, we are actually generating precisely the polynomials that we listed over here. Now, we don't want to generate all of the polynomials. That's going to become a bit lengthy. So what we'll do is we'll set x is equal to y is equal to t. And if we do that, well, the 1 stays 1, but x and y are both t, so we get 2t. And x squared, xy, and y squared all become t squared, so we get 3t squared. So what you can see is, after setting x equal to y equal to t, the coefficient of t to the n counts how many polynomials you can make of degree n from these two variables. The 1 over 1 minus x and the 1 over 1 minus y just becomes 1 over 1 minus t squared. And you could now expand this in a power series, and the coefficient of t to the n solves exactly the counting problem that you want. So Cn is equal to the number of degree n polynomials of two variables. So this was a very simple counting, but it forms the heart of what we'll do next. And in fact, all of the proofs for Hilbert series can be done in the way that I've just shown you over here. It's just simple logic of this type. So I'm going to suggest some exercises that you might want to try. So here's one simple thing you could do in blue here. Prove that dm, defined by this power series expansion, so you've got 1 over 1 minus t to the q is equal to this expansion, and dm multiplies t to the m. Prove that that counts how many degree m polynomials you can write in q variables. Now, how does this generalize if our variables obey some constraints? And a nice problem with constraints amounts to counting the number of spherical harmonics on a sphere. So let's start off with just a one-dimensional sphere, a circle. So we've still got x and y, but for the circle, now our x and y are not independent variables. In fact, x squared plus y squared is equal to 1. That's because we're on a circle. So if we now look at what polynomials we've got, well, degree 1, we've still got degree 1. Degree 0, 1 still gives us 1. Degree 1, we've still got x and y, good. But for degree 2, now we've got x squared, xy, and y squared. And x squared and y squared appears inside our constraint. So we should properly just rearrange these a bit into x squared minus y squared xy, and we do not count x squared plus y squared because our constraint sets that equal to 1. So in degree 2, instead of counting 3 independent polynomials as we had before, we now only have 2 independent polynomials. So by just counting and ignoring the constraints, we overcount. So we have to correct that. We have to somehow subtract off that overcounting. And I'm just going to tell you how it's done, but I'm telling you, you can prove it exactly as I proved the first Hilbert series that I looked at. So this is a really nice exercise to do with a piece of paper and a pen and make sure that this formula is true. So what you would do is, this is for a sphere SD. So if we have SD, so what is an SD? An SD would be x1 squared plus x2 squared plus all the way up to plus xd plus 1 squared is equal to 1. So for the S1, we had 2 variables. For an SD, we would have d plus 1 variables. Because we've got d plus 1 variables, the denominator looks like 1 minus x to the power of d plus 1. In the numerator, we've got 1 minus x squared. The coefficient of this x squared is a 1. So here there's a 1 multiplying the x squared. And that's because we have one constraint, just this constraint sitting over here, x1 squared plus x2 squared plus dot 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 plus xd plus 1 squared. And secondly, this constraint is degree 2. And that's why we have this x squared sitting here with degree 2. Okay? So you should try to convince yourself that this is the correct Hilbert series, but let's check it. Let's make sure that this works. If you plug in d is equal to 1, so I'm just going to plug values of d into this formula and expand it. I used Mathematica. So I plug d is equal to 1 into this formula, I expand it, I get 1 plus 2x plus 2x squared plus 2x cubed, it keeps going, plus 2x to the L. Why is this the case? Well, we're on a circle. On a circle at any angular momentum L, you can either go clockwise or counterclockwise. So those are the 2's that we're counting. Those are all of the angular momentum modes. Now let's look at d is equal to 2. For d is equal to 2, we would have 3 variables, x squared plus y squared plus z squared is equal to 1. And for d is equal to 2, this is the usual problem that you have in non-relativistic quantum mechanics. So you'd be counting the spherical harmonics of non-relativistic quantum mechanics now. And when you work out what is h2 of t, when you do the series expansion, it's 1 plus 3x plus 5x squared plus 7x cubed and so on, plus 2l plus 1 times x to the l. And what's going on here? Well, you know the answer. For the angular momentum multiplet of angular momentum L, we have 2L plus 1 states. And that's basically because the state is labeled by 2 quantum numbers, L and M runs from minus L up to L. What about for D is equal to 3? So the expansion is 1 plus 4x plus 9x squared plus 16x cubed and so on. And for x to the 2L, it's 2L plus 1 squared. And I think this case will also be familiar to you. For an S3, what do we have? We have x squared plus y squared plus w squared plus z squared is equal to 1. So we're dealing with the group SO4. But when you work out representations of the Lorentz group, you probably did a Witt rotation to turn SO13 into SO4. And then you decompose SO4 into SU2 times SU2. And that's a correct statement. You know, SO4 is SU2 times SU2. And the spin 2L representation of SO4, that is the degree 2L polynomial. This has got spin L, L of SU2. But, you know, the representations of SU2 are the same as representations of SO3. And you know that an angular momentum L representation of SO3 has dimension 2L plus 1. So this 2L plus 1 sitting here is exactly the same as the counting that we did in D is equal to 2. So you could now plug in whatever you want. If you've wondered how many, you know, spherical harmonics would there be on a 10-dimensional sphere, well, you would just plug 10 in for D into this formula, go ahead and expand it, and you would learn how many spherical harmonics there are for each angular momentum. Now, let me tell you what the rule is. So if you have a polynomial ring or that's being generated by n1 generators of degree 1, n2 generators of degree 2, and so on, and then m1 constraints of degree 1, m2 constraints of degree 2, what is the Hilbert series? Well, look at the denominator first. So for each of these generators, so the generators are what tell you about the denominator. So if we've got denominators of degree 1, then we have a t sitting there. If we've got generators of degree 2, we've got a t squared sitting there. If we had generators of degree 4, we would have a t to the 4 sitting there. And the power that we raise it to over here is the number of generators. So knowing how many generators you have of whatever degree, you could immediately put these factors in the denominator down. And by degree, we mean what we always mean with polynomials. Count how many letters are being multiplied, okay? And then look at the numerator. We start with a 1, and then we say minus m1t1. This m1t1 is for m1 constraints of degree 1. This m2, well, that's counting how many constraints, and the 2 is for degree 2. So you can very easily write down the Hilbert series, and this allows you to do the counting in the polynomial ring for any number of generators, any number of constraints. Now, just like in gauge invariance, my discussion was a little bit simplified. Here it's also simplified, and I'll tell you where's the simplification, just so that you have some idea. So why did we need to subtract these terms in the numerator? It's because we were overcounting. Why were we overcounting? because now we had constraints like this x squared plus y squared is equal to 1, which meant that not all of our variables were actually independent. Now, it can turn out, so not all of our generators are independent. Now, it can turn out that perhaps not all of your constraints are independent. So there might be relations between the constraints that you've got. When you've got relations between constraints, mathematicians talk about syzygies. So the first syzygy would be the first constraint among the constraints, and you'd now need to add a plus term in the numerator for all of the first syzygies. But the first syzygies might not all be independent. There might be relations between them. And then you would have to add in second syzygies, and those would come with a minus. And so it keeps going. And one of the big achievements by Hilbert, this is the same Hilbert of Hilbert space, is a result called Hilbert's syzygy theorem. And what Hilbert's syzygy theorem tells you is this process truncates. So you can't just keep having syzygies of higher order. There's some highest order for the syzygies, and it's bounded by how many variables you have in your polynomial ring. The reason why I didn't go into that in too much detail is that next week we're going to be computing the Hilbert series of this matrix quantum mechanics. That's going to let us see what the generators are and to interpret what the complete space of gauge-invariant operators is. And what we will find is, remarkably, our generators are not constrained. We generate the full space of gauge-invariance freely. So we won't even have these minus terms. But remember that that numerator is telling you something important. Our numerator won't simply be a 1, but we'll see next week what it is. And if you mess around with Hilbert series this week and just try to count a few things, you'll get a much better idea of how to interpret these things. So we'll be calculating partition functions and interpreting them the way that mathematicians interpret Hilbert series. So, okay, so that's the end of the second thing I wanted to discuss. So I don't know if there's any questions now.
Yeah, that's just a silly question from me. So when you talk about degree of a constraint, that means that the constraint needs to have a particular form, but obviously not, you can't have, not all constraints in physics are polynomials. So what?
Okay, so great, so very good. That's absolutely true. So if you try to invent a, so let's say, so before we had x squared plus y squared was equal to 1, so that was nice. But what happened if you wanted to study a constraint that said x squared plus y cubed is equal to 1 or something like that? Now the two terms are not the same degree. Well, sorry, if you want to study that problem, you're on your own. The mathematicians cannot tell you very much. They can only study the problems where things can be graded nicely. So that's a harder problem. So indeed, even in physics, you might wonder, you know, how useful will this be? And that's a great question. So if I don't comment on this, make sure to ask me next week. So here's my claim. I hope it sounds provocative and unlikely. Because if it sounds provocative and unlikely, then hopefully you'll ask me next week. Here's my claim. I claim that I'm going to prove all kinds of results for this free theory. This is just an oscillator. So I'm going to study this harmonic oscillator of matrices. I'm going to prove all sorts of results. And then I'm going to shamelessly claim that this will hold for any interacting theory, no matter how large the coupling strength is. And so you better stop me from making that claim without challenge.
Deal.
I think Coleman says that the life of a theoretical physicist is treating the simple harmonic oscillator with greater and greater degrees of abstraction.
That's right. And apparently Jakif says, so Coleman was always trying to reduce everything to harmonic oscillators. And apparently Jakif said Strominger is trying to reduce everything to black holes.
Ah,
so
good.
Yeah. So, okay.
You unify them.
Sorry?
You will unify them.
Yes, indeed. I didn't think about that, but yes.
I just have a quick question.
Yeah.
So these syzygies, so I've been looking at superconformal indices a bit lately, and So, for instance, when one is considering, you will have fugacities related to each, say your rank,
Oh, sure.
the weight of your
Good.
for the gauge group, and these have to essentially have a relationship where you have like a fugacity x1 to n. You have to have a product from
Right.
those have to be equal to 1. Is this somewhat related to these kind of problems?
Oh, absolutely. So the kinds of Hilbert series that appear for indices of superconformal theories are usually more complicated. Usually you'll get a denominator there that exhibit both plus and minus signs, and they really do reflect constraints obeyed by the operators that you're counting. What we'll see next week is I only have plus signs in the numerator, and it was a little bit of a surprise that that came out like that. This is, I mean, a very, very simple type of Hilbert series that we're going to get. So, but indeed, for the superconformal indices, I don't know how many Hilbert series you've calculated, but any of those numerators that have plus and minus structures are because you've got constraints and syzygies.
Okay.
Yeah. Great.
I just want to check, could that, so you are just doing partition, these are partition functions, so they're not graded like an index. Is that correct?
So I can introduce more sophisticated grading, but it turns out that the decomposition that we'll be using only works if you grade by degree and nothing else. So we'll be using something called a Hironaka decomposition, and the Hironaka decomposition doesn't survive if you have a more sophisticated grading. You should just grade by degree.
Okay, thank you.
Sure. Okay, so now the last thing I wanted to discuss are called trace relations. This also goes back to Hilbert, in fact. So Hilbert explained that trace relations always arise by symmetrizing d+1 indices when each index takes only d values. That'll always give 0. And I want to give you an example now to illustrate this. So our example, we're going to set d is equal to 2, okay? And let me give you an example of a trace relation. So take A, B, and C. These are any two 2x2 matrices. So you can make up any 3 2x2 matrices that you like, and now plug them into this equation sitting over here. So we'll take trace A times trace B times trace C minus trace AB, trace C, and those are the 4 terms. And if you sum those, you will get 0. Okay, it doesn't matter what you chose for A, B, and C. The only thing that's important is that they're 2x2. So why does this work? So first of all, why is this related to, oh, sorry guys, here's a typo. I shouldn't have said symmetrizing, I should have said anti-symmetrizing. Yeah, so we have to anti-symmetrize, good. That was a little test for the audience, you guys. Pay attention. Okay, now, let's explain why is this equation over here related to anti-symmetrizing. So I've written all of the matrix indices out here using the convention that, as usual, repeated indices are summed. So if you've got trace A, trace B, trace C, this is A, I, B, J, J, C, K, K. For the second term, I've got trace A, B, trace C. So how do I write trace AB? Well, this is IJ, AIJ, BJI. So that's trace AB. And then trace C is just CKK. And let me maybe also look at this term over here. Okay, so we'll look at this term over here, which corresponds to this term over here. So this is trace ABC. I've got AIJ, BJK, CKI, trace ABC. Now, how do I get the second term sitting here? How do I get this term from the first term? Look at the column indices. I swapped the column indices of A and B. So the J of B has gone to A and the I of A has gone to B. I did one swap on the column indices. Because I did a swap, when you anti-symmetrize, every time you swap, you must include a minus. Look at the term underlined in blue. Now, what do I have to do to the row indices? Well, the first thing that I have to do is first I should swap I and j. That puts the j onto A. Now there's an I on B. And then I swap the B that's on I with the K that's on C to get the 3 indices here. So to get this particular term, I need to do 2 swaps. I'm just looking at the column indices now. So I have to go, so for this term here, what do I have to do? So let's maybe put it, well, I think I can do this. Oh, no. Okay, so we can do this. We had I, J, J, K, K. Those were the indices on the ABC above. Now, first I'll swap I and J. So I've done one swap. So these two swapped. And now I will swap I and K. I, J, J, K, K, I. So then I did a second swap. Okay. So in this term, to get this term, I do 2 swaps. So that's why it's a plus again. So these 6 terms sitting over here, they are just obtained by anti-symmetrizing the column indices. Okay. Now, why is this identity true? It's actually true because when you do these sums, you are, when you do the sums, every term in the sum, every term that you're adding is a 0, and a sum of a bunch of zeros is 0. Okay, so let's pick one term. We could have picked I is equal to J is equal to K is equal to 1, but then it's just a bit trivial. Every term has got a 1 for the indices, and that obviously cancels to 0. Well, the least trivial thing we can do is let's pick 2 indices the same. So I is equal to J is equal to 1, and we'll make K equal to 2. So the indices are not all the same. So I've just taken these values and plugged them in. So for example, the first term sitting is AII, that's A11, BJJ, that's B11, CKK, that's C22. Okay? And if you now look at these terms, this first term sitting over here, the A11, B11, C22, cancels against the A11, B11, C22. This term sitting over here cancels against that term sitting over there. And this term sitting over here cancels against that term sitting over there. So it's 0 for any 2x2 matrix that you pick up. Now, previously I said I'm going to be proving results that will hold no matter how strong the coupling is. The secret of why that's always the case is that the identities that I'm going to be using are always trace relations. And trace relations are just simply true statements. They're sort of kinematical. They've got nothing to do with dynamics. Doesn't matter how large the coupling is, this trace relation will always be true. Why is it so useful? If we were to put A is equal to B is equal to C, our trace relation becomes the statement that trace A cubed minus 3 trace A squared trace A plus 2 trace A cubed is equal to 0. And that means if you know trace A and you know trace A squared, then you can calculate trace A cubed. And this is the kind of a thing that we're going to be doing the whole time to generate the complete space of gauge-invariant variables. And that's the story behind trace relations. Okay, so I'm going to end with just, I'll give away the punchline of next week's talk. But before I do that, are there any questions on these trace relations?
The challenge for you guys have seen me write on web tracks, prove this using web tracks.
So yeah, you can.
You end up with a product of a symmetrizer and an anti-symmetrizer that kills each other.
Right, absolutely. So that would be a perfectly fine way to do it. Absolutely. So let me tell you what is the punchline going to be of next week's talk. When you study this matrix, these systems of matrix quantum mechanics, there are many conjectures that these systems should be relevant for the description of black holes. And you should somehow see a black hole appearing. Now, next week, what we're going to see is we're going to reduce our gauge theory to just the gauge-invariant variables. And then we're going to find out with this set of generators, we can generate the complete space of gauge-invariant variables. But there's two types of generators that appear. There's one kind of a generator called a primary invariant. And when you build your gauge-invariant operators, you're allowed to take, or you must take, the primary invariants to any power. So you can raise them to any power. So the primary invariants are generating for you a Fock space. This is just like the A daggers. You raise those to any power when you want to build the full Hilbert space. And you've got some invariants that are just like that. You raise them to any power, they act freely. But then there's a second kind of invariant, a secondary invariant. And it turns out that you can use a secondary invariant only once. And you can only use one secondary invariant. So either you have no secondary invariants or you just have one secondary invariant. So this doesn't look like a perturbative degree of freedom. It doesn't look like a Fock space structure. This looks like a non-trivial background. So it would be nice to interpret this as a black hole microstate, and the perturbative degrees of freedom, you can then just put gravitons into this black hole microstate. Now, if you really believe that, you would want to show that the growth of these secondary operators matches the entropy of a black hole, because if you count the number of states and take the log, you should get n squared. That's what we expect for the entropy of the black hole from gauge theory gravity type analyses. And when you actually calculate how many secondary invariants there are, it grows like crazy. And when you try to fit a curve to it, e to the n squared fits extremely well. When I said grows like crazy, when you go, say, from n is equal to 2, you've got 5 primary invariants, you've got no secondaries. When n is equal to 3, you have something simple like 8 primary invariants, 1 secondary. When you get to n is equal to 7, you've got something like about 50 primary invariants and a number with 16 digits for the number of secondary invariants. So it just grows like crazy. So the proposal next week is that by completely gauge fixing to the gauge invariant degrees of freedom of this matrix model, we actually are able to identify what is a very plausible definition for the black hole microstates, and it reproduces the correct entropy. And so that's all I wanted to say.
Amazing. I think you were the first speaker in the however many years we've been doing this who actually finished on time.
I was watching the clock.
We've had several questions during the talk, but we can have any further questions now. Yeah, Ben.
So I just want to try and understand the Hilbert series that basically counts how many degrees of freedom, or gives you a way of counting how many degrees of freedom in the gauge invariant theory.
Exactly. Yeah, that's so okay. So what it does is it counts how many degrees of freedom, but it also tells us exactly how those degrees of freedom are built up. Because if you look at the Hilbert series, I'm gonna get this Hilbert series by actually calculating a partition function in quantum field theory. And when I take a look at this Hilbert series, then by looking at the denominator, I know how many generators there are. And these guys in the denominator I can raise to any power. So they really like a Fock space. The stuff that sits in the numerator, that's going to be where my secondary invariants come in. And they're going to tell me how those act inside the space of gauge invariants. So not only do I count the gauge invariant degrees of freedom, but I also get a very nice idea what the structure of these gauge invariants is and how to generate the complete space in terms of some generating set. So that's what the Hilbert series is going to be giving me.
This for like non-holonomic constraints?
What's a non-holonomic constraint?
Like a derivative on a constraint. So
there's no derivatives here. So my gauge symmetry here is going to be this one. Phi tilde is equal to u dagger phi u. That's my gauge symmetry. So I want to find out what are the invariants under that transformation. And well, there's no constraints. We're going to find that there's a nice decomposition of this ring, and there will be no constraints. It's all generated freely, just like you would expect if you had a Fock space with a number of different backgrounds.
Maybe part of, I think what's going on here, Robert, you're working in a zero spatial dimensions, right? There's no spatial dependence on what's going on.
Right. Yeah, it's matrix quantum mechanics. So there's T. So all of my fields will be a function of T. So there's the Hamiltonian, no space integral. Okay. So this matrix quantum mechanics, a system like this, if you have 10 matrices, is meant to give you a description of 11-dimensional M theory, plus fermions and stuff that I didn't add in. So the actual number of dimensions that this theory has is kind of hidden in there. It's holographic. They emerge from the description. But these degrees of freedom over here are just quantum mechanical.
Super, thank you. And then Daniel.
Yeah, I just had a question about the trace calculations you were doing at the end. I think I missed. Why specifically were you restricted to 2 dimensions for this case? Where did that?
Oh, good. So I just chose 2 as the simplest example of how this would work. If I wanted to work with, say, 3x3 matrices, then in fact I would have had to anti-symmetrize 3 indices. And instead of getting 6 terms to 3 factorial, I would have gotten 24 terms, 4 factorial. So it's always just d plus 1 factorial. That's how many terms appear. But there's trace relations for any n.
Great. Question from Jared online, or any last questions from the audience? Yeah, if not, then let's thank Robert once more.
Thank you.
Amazing, thank you so much. And we look forward to seeing you next week.
Sounds great.